Hello, my friends. Chris here with ISK Recording. I hope you are having a wonderful day today. We're going to talk about preamps, and I love preamps, so I could just talk about this all day long, but I'm not gonna. I'm going to keep it concise, and we're going to talk about the important things that you need to know about a preamp. We're not just going to talk about the basics. We're going deep in this lesson. We're going to talk about what a preamp is, what it does, how it works, and how to properly set the gain. So first off, we're going to talk about why the preamp is necessary. You see, the job of a preamp is, in technical terms, to boost a signal from microphone level to line level. So what's microphone level and what's line level? Well, microphone level is the very weak signal that comes out of this microphone. And line level is the standard signal level that most audio equipment uses for sending and receiving audio signals. A line level signal is roughly the same amount of power as a headphone output. It's about 1.5 volts. It's not enough power to drive your speaker system, but it's enough power to hold all the information and keep the noise floor really low. For instance, here's an analog compressor. You see, it has a line level input and line level output. Here's a standalone analog to digital converter. Again, it's optimized for a line level input. Any audio interface will have the analog to digital converter built in, but the signal from the microphone still needs to go through a preamp to be optimized to line level before it can go through the conversion. So what would happen if we didn't plug the microphone into a preamp? Well, like I said, the signal coming from the microphone is very weak. And what happens is the converter circuitry actually adds a small amount of noise. It has its own noise floor. So what we need to do is overcome that noise floor by a considerable margin so that it's no longer a factor in the sound quality. See, if I just plug this microphone straight into the line input without the preamp, the signal coming out of this microphone would be roughly the same volume as the noise floor of the converter circuitry. So sure, it would work. You'd be able to hear the sound coming from it, but you'd have to boost the volume in your DAW, and you'd be boosting the noise floor significantly, and it just wouldn't sound good. So I need to use a preamp. So I'll plug my microphone into the preamp. The microphone I'm using here is an ISK ICDM, and as I turn the gain up, I get louder, and as I turn the gain down, I get quieter. Turning it up, turning it up, turning it up, turning it down, turning it down, turning it down, 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 turning it up, turning it up, turning it up, turning it down, turning it down, turning it down. The signal chain here is the microphone is plugged into the preamp. The output of the preamp goes into the line input of my audio interface. Now, if you have an electric guitar or an electric bass guitar, the output from these instruments is a similar level to a microphone output, except there's some differences. It's a high impedance, unbalanced output, whereas a microphone is a balanced, low impedance output. So, in order to optimize the output of an electric guitar to go into a preamp, that signal needs to be converted from high impedance unbalanced to low impedance balanced. And then you can plug it straight into the XLR input of the preamp. So to use this, we use what's called a DI box. If you want more information about the differences between these signals, check out lesson 11 on analog audio cables. So what's a DI box? It has a 1/4-inch input that the guitar gets plugged directly into, and it has an XLR output that gets plugged into the preamp. And the DI box does all the work of converting the signal to the proper type. Now, some preamps actually have a high Z input, and high Z stands for high impedance. So you can plug your guitar straight into that 1/4-inch input on the preamp, and it's already optimized to receive that high impedance unbalanced signal from the guitar. This method of recording electric guitar is called direct inject, or DI. That's why it's a DI box. And it's used for capturing the raw signal from a guitar, which you can then use software amp emulation, or you can reamp later to get the sound that you desire. Now, there's a lot of different features on various preamps, but the one feature that all preamps have is a gain knob. This obviously controls the volume of your output, but the way it works internally within the circuit is actually a little bit less obvious. It actually works through gain reduction. You see, the actual amplification circuit is always providing maximum gain 100% of the time. And the gain knob is simply a variable resistor that trims it down to the desired output level. Let's take a look at the basic concept of how Class A amplification works. And by the way, a side note, because this bugs me, Class A amplification circuit just refers to the type of circuit that it is. And I want to point out that absolutely all microphone preamps use a 100% Class A design. There's not a microphone preamp on the market that does not use 100% Class A. A lot of preamp manufacturers boast about their 100% Class A design. Well, it's not really something to boast about because they're all a Class A design. It just wouldn't make sense to use a Class B or a Class D design on a preamp. Class B and Class D designs are both meant for higher power outputs. They're mainly used in power amps for large speaker systems. So, audio amplification is actually all about controlling an output voltage. It uses an input voltage to control an output voltage. Let's take a quick look at how voltage is turned into sound. Right here I have a speaker, and if I apply 9 volts to the terminals, as you can see, the speaker pushes out. Now if I reverse the polarity and apply 9 volts to the terminals, as you can see, the speaker pushes in. Now if I double the voltage, I'm going to put two 9-volt batteries in parallel. So now we've got 18 volts. I'm going to connect that to the speaker terminals. Okay, as you can see, it sucks in, but it sucks in twice as far with 18 volts as it did with 9 volts. And if I reverse the polarity, "18 volts pushes it out twice as far as 9 volts does. So the more voltage, the farther in and out the speaker goes. Now what I can do to have precise control over the movement of this speaker going in and out is I can put a variable resistor in the path. So as you can see, by controlling this variable resistor, I'm actually controlling how much voltage is allowed to pass through to the speaker, and therefore control how much the speaker moves in and out. But what if, instead of using my fingers to control this variable resistor, I could just use electricity? I could use an electrical current to control that variable resistor. Well, that's how an audio amplification circuit works. A very weak input signal controls basically a variable resistor, a valve. We'll call it a valve because it's allowing a certain amount to flow or not flow. So a very weak input voltage can control a valve that controls the output of a higher supply voltage. So the original input current, the original signal, all it's used for is to control this here valve. And the valve will replicate the same fluctuations of voltage, and the end result is a duplicate of the original signal, but at a higher voltage. So there's two types of components that can be used as a valve: a vacuum tube, which is actually sometimes called a valve, or a transistor. In a vacuum tube, the physical space where the electrons are being controlled is encapsulated in a glass tube, and it's a complete vacuum. There's no oxygen, there's no air, there's no chemicals, there's no gases, there's nothing in it. Everything is sucked out. It's a vacuum. That's why it's called a vacuum tube. In the other component, the transistor, the physical area where the electrons are being controlled is made of silicon. It's a material that is solid in its state, hence the name solid state. So we have vacuum tube and solid state topologies. And these represent the two different categories of audio circuits used for amplification. So even if it's not an amplifier, it might be an EQ or a compressor, the tube is still doing amplification. So in an EQ, the signal actually gets weakened and it has to get amplified again for the output. So it goes through either a tube or a transistor in the amplification stage. So yes, an EQ still has an amplification circuit built in. A compressor still has an amplification circuit built in. Tube gear is often associated with vintage equipment, and many people hold the opinion that it sounds better. I personally think better is the wrong word. I find the sound quality from both topologies to be equally as good, but there are some differences. So with tube gear, I'm going to put the sound into two different categories because there's two drastically different types of circuit designs that are used with tube gear. Category 1 is what a lot of people call warm sounding, or they say it has character. It kind of rolls off the high frequencies and there's a little bit of noise and It's not really high fidelity. And this uses the starved plate design. You see, the starved plate design came about because tube gear is expensive. So this design came out as a way of giving people the option of having a tube in their audio path at a much lower cost. Because a lot of people believe that just adding a tube to their signal path will magically make everything sound better. As you remember from our previous example with that speaker, our supply voltage was 18 volts. Well, for a vacuum tube to operate optimally, it needs a supply voltage of roughly 250 volts. But then you need an expensive power supply, and once you've got the expensive power supply, you might as well have everything else expensive. So a starved plate design starves the plate of the high voltage that it needs and only gives usually about 50 volts to the tube. It's enough power for the audio to pass through, but the tube doesn't really provide any real amplification. It's just there as a gimmick. Usually in these designs, the real amplification is happening with solid-state components, and then they just throw a tube in the signal path for marketing purposes. Now, the second category of tube amplification circuits is the proper one that sounds really good. It's the high voltage design. Like I said, these use an input voltage of about 250 volts, and the power supply required to provide that input voltage is fairly expensive. And if you've got an expensive power supply, you're likely going to use higher quality components everywhere else, such as a higher quality tube, which will give more fidelity, higher quality output transformers, better capacitors, just better everything. And that'll result in a more accurate sound reproduction. So if you're researching tube preamps, how do you tell if it's a starved plate design or a high voltage design? Well, the first way is to look it up in the manual. You can usually find the rail voltages. So if it's got more than 200 volts of rail voltage, then it's a high voltage design. If it's less than like 100 volts, then it's a starved plate design. And you'll also want to check the manual to see if it specifically states 100% tube amplification. If it doesn't say this, it could be a hybrid design that uses both solid-state amplification and tube amplification. And in these cases, usually, most of the amplification is done by the solid-state components, with the tube just being there to either add tube value or for marketing purposes to put the sound through a tube. But what really matters with the tube is how much voltage is supplied to it. And then another indicator is the cost of the preamp. If it's a tube preamp that costs less than like $600, it's most likely a starved plate design. And if it costs more than $1,000, it's a pretty safe bet that it's a high voltage design. As I demonstrated earlier with the speaker, an audio amplification circuit actually makes a replica of the original, and the replica is at a higher voltage. So the more accurately it can replicate the original, the better quality it is. But there's two components to that. There's replicating it accurately, and also what the really nice tube circuits are known for is adding some nice harmonics. That's a pleasant coloration to the sound. That's not like noise. It's a certain openness, and it's very natural. You can't even really tell that it's happening. It's more of a feeling. Now, all amplification circuits add noise. It's measured as the EIN, equivalent input noise. I'm going to talk a little bit more about that later, but for now I'm going to talk about what the difference is between that noise from a tube circuit and a solid-state circuit. You see, a solid-state circuit will actually have less noise. They're cleaner, but the noise that is there is not second or third order harmonics. It's random. It's like a white noise. So let's say our input is the middle C on the piano. And if we just add random noise to that, that's like mashing a bunch of keys along with that. It's rather unpleasant, and it doesn't add anything nice to that sound. But with tube amplification, if our input sound is the C, the noise that's added isn't random. It's harmonic. So it's like adding musical notes that enhance the original. When you look at a preamp's specifications, you'll notice tube preamps have more noise and solid-state preamps have less noise. But as I just explained, that noise from the tubes is nice, whereas solid-state offers a cleaner, more accurate sound reproduction. Inexpensive solid-state preamps can still sound fantastic. Every audio interface in the market that has built-in preamps uses solid-state designs in their built-in preamps. Now, when I'm researching preamps, the main specification that I'm looking out for is the EIN. I touched on this already. It's the equivalent input noise, and that's how much noise the preamp generates and adds to the signal. You know when you plug your microphone in and you need to turn the gain up, so you're turning the gain up, and you're getting this white noise, this hiss sound as you turn the gain up? Well, that's the EIN. And some preamps add more of that than others. And ideally, you want to have as little of that as possible. So the lower the number, the better. But keep in mind that this number is specified in the negatives. So a negative 130 is lower and better than negative 129. Now, there's a standardized testing method for coming up with this number so that all manufacturers are on a level playing field and the consumer can get accurate information. Now, some manufacturers might skew the testing method just a little bit to try and make their numbers look better. So what you want to look for on the EIN specification is that it's measured A-weighted with a 150 ohm load. If it does not say those two things, then there's a chance that the test was manipulated. Kind of like testing how fast a car can go, but secretly performing the test going downhill. So you want A-weighted and 150 ohm load. Now, using this testing method, the theoretical lowest possible noise floor is minus 133 dBu. And that's actually the amount of thermal noise that's generated just from a single resistor. So it's not possible to get lower than that. Right now, the preamp that I have this microphone plugged into is a Cranbourne Audio Camden EC2. This preamp has the lowest noise floor of any preamp I'm aware of on the market, and it's specified at 131 dBu, A-weighted, 150 ohm load. One of the quietest tube preamps on the market is the DW Fern VT2, and it has an EIN of negative 124 dBu. I also like this preamp here. It's the FMR Audio RNP, really nice preamp, and it has an EIN of negative 120 dBu. Okay, now we're going to talk about how to set your gain to the optimal level. A lot of people have different strategies on how to do this. There's a lot of good strategies out there. I'm just going to show you my strategy, but regardless of which strategy you use, there's certain rules that apply. So you don't want it to be too quiet because you want to optimize your signal to noise ratio. And you don't want it to be too loud because you only have so much room available, and if you go over that, you're going into clipping, and that's going to sound bad. So my strategy is super simple. I just look at the size of the recorded waveform. If it's too loud, you can see that it's clipping. And if it's too quiet, you can hardly see the waveform at all. Let's take a look at some electric guitar here that I recorded. So this first one, this is definitely too hot. This is what you don't want to see. You don't want to see flatlining anywhere because that's going to cause audible distortion. And even all along here, like it's still not clipping, but there's no headroom. Like right there, it clipped a little bit. And then here it's clipping pretty hard. This is too hot. You want to turn your gain down if your waveform is looking like this. This here, well, this is not too bad, but it's still a little bit too hot. You still want to turn it down because that almost clipped. You want to have a little more headroom than that. And right here, it actually did clip. You see, for most of his levels, it's actually pretty good. But you want to have your gain set low enough so that it works for the majority of the recording. And also when they go and play something extra loud, like in a loud part, you don't clip. That's the most important part right there. No clipping allowed. So if you turn your gain down a little more, there we go. This is a pretty nice recording level. This is about as loud as you would want it. So in the normal volume sections, there's more than enough gain here to get a good signal to noise ratio. And he can go and play loud, and there's still lots of headroom. Even in these loud parts, there's lots of headroom that he could play louder, and you're still not going to go into clipping. This one here, this is what I would call pretty much an ideal gain setting. You're still way above the noise floor, even when they're playing quietly, and there's tons of headroom. And then even if you set your gain a little higher than this or a little lower than this, like this is good. And then this one here, this is about the lowest setting you would want to go. This is still perfectly acceptable. But I just wouldn't go any lower than that. Like this here, this is a little bit too, you're starting to get into the range where the noise floor from the conversion, it's not an issue. It's still extremely low, but I mean, you don't want it to be there at all. So I would go just a little bit higher than this. Like I said, at least to this. So yeah, I would recommend setting your levels anywhere between this and this to be ideal. I mean, this one here is not bad. Like, that's not really going to be noticeable. That like tiny little bit of clipping like that is not bad, but there's no reason for it. There's absolutely no disadvantage. There's no loss in sound quality from going to a recording level of this here. Like there's just no difference in sound quality from this to this. So there's no reason not to record lower so that you avoid clipping. That clipping is no good. So if you found this video helpful, please hit the thumbs up down there and give this video a like. I would really appreciate that. Also, you can subscribe to this channel because I'm coming out with lots more videos. I'm uploading an entire audio engineering course and every once in a while a little video about certain topics here and there. So subscribe and then you'll get all that content free of charge. I'll see you in the next video, which is about analog to digital to analog converters, tell you what they are, why they're important. And we're even going to do an experiment so that you can hear with your own ears what the sound quality is from going out and then back in. We're going to do it several times to really exaggerate that difference, and you'll be able to see how many times we went in and out and hear what the difference is. All right, anyways, enough about that. You have a great day. I'll see you later.